Hello! Thank you for joining our Climate Action Network event today. Happy spring and happy Earth Month. This month, April, we have lots of great events for you scheduled. And today we have a guest speaker, Andrew Michler. Andrew concentrates on designing passive homes, and we'll be hearing from him today and learning all about passive home design. My name is Jessica Klein, and I'm a member of the Climate Action Network here at EXP Can, and I'll be hosting the event today. Just a quick note, we are broadcasting live in EXP World, EXP Workplace on the EXP Can page, and also live on YouTube. The session will also be recorded, so you can watch it again later on YouTube also. If you have questions, go ahead and drop them in the chat bar where you're watching the video today, and we're going to save some time at the end to address your questions, and Andrew will answer those for you. For those that don't know much about EXP Can, the long name is EXP Climate Action Network. We're a group that started in July of 2022, and we're a group of agents, brokers, staff at EXP, and partners that we are enthusiastic about caring for our environment, and our goal is to provide a safe space to network and educate, collaborate, and inspire climate action on all levels. And one of the ways we do that is through educational speaker series like the one we have today. When you join the EXP Can team, there are opportunities for leadership, for project management, graphic design, and hosting events like the one we're doing today. As I mentioned before, if you have questions throughout the speakers series today, please drop those in the chat, and we will answer your questions at the end. Now I'm going to introduce and talk a little bit about our presenter today, Andrew Michler. Andrew is focused on high-performance building design and materiality since 1995. He's the principal of Hyperlocal Workshop. Andrew has written and researched extensively on contemporary architecture and is the author of the book Hyperlocalization of Architecture. Andrew is the co-founder of Passive House Rocky Mountains and previous board member of the Passive Home Network. He was also the chair of the Northern Colorado Renewable Energy Society. Andrew completed the first international certified passive home in Colorado in the year 2016, and it won the Green Homes Award from Green Builder magazine. Additionally, Architects Newspaper Small Spaces Award for the mobile espresso bar Soul Coffee, and he'll tell you more about these projects today also. Andrew is also partnering in the development of Restore Passive House, a market rebuilding project for the Marshall Fire that's being featured currently on NPR and PBS's Nova. So with that, I'd like to bring Andrew on. Hi, Andrew.
Hi there, Jessica.
Thanks for joining us today.
Sure.
As we get started, I wanted to ask you a couple quick questions. Why are we talking about passive homes today? Why do you think it's important?
Well, I think the first thing is it's actually called Passive House.
Oh.
And the reason is because it's not just for homes, it's for all types of buildings, including not just residential, commercial, any kind of building you can think of can be a passive house. And what we're talking about is a building standard that kind of developed in Germany, but they're looking at how do we make climate adaptive buildings and how do we create a standard so we can build these types of projects all over the world and be consistent with how they perform in all sorts of different climates. So it's very climate specific, but it's also universal. So it was about the scalability of the problem of climate appropriate building design. And then the other side was how do we make buildings really comfortable and healthy? And how do we kind of go beyond what we traditionally think about, and how we provide fresh air for the occupants all the time? You'd be surprised how unfresh the air is in many buildings, of course. And also the comfort around buildings, not just putting equipment in. Comfort's really about the holistic view of how the building works in the environment. So those are the main characteristics of a passive house.
Great. I'm excited to learn more. I already learned it's passive house.
Yes, yes.
Passive
No,
house.
it's always the first thing to talk about what it means, because everybody thinks it's a little house. I'll go into that a little bit, but we can look at all sorts of different types of ways to approach it.
And before, I know you have a great presentation. Before we dive into that, I was wondering, what are one or two things that you really hope our audience of realtors will take with them today?
So I guess the main thing is that the building industry, especially around sustainability, is a pretty massive amount of information. It can get pretty detailed pretty quickly, but I really want to hope we could kind of look at some of the outcomes. Of course, there's always the carbon question: how much our buildings use, impact on the atmospheric carbon side. But there's also the idea of resilience. How do our buildings survive kind of more extreme events like Marshall Fire, for instance, and other things? And then, of course, there's the comfort things, like how do we take all these things but maximize the quality of the space inside for people, so that it's like irresistible to be in. So that's hopefully some of the outcomes that we'll be talking about.
Great. Well, as I mentioned, everyone drop your questions. We'll answer them at the end. And Andrew, take it away.
Okay. Let me do the share screen. Let me do my share screen here. Okay. And just for confirmation, are we seeing my screen? There it is. Great. So, yeah, so you heard my bio. I work mostly on residential projects, and mostly mountain projects, because the first passive house I did was my own. So a lot of people see that. And so I tend to get a lot of people who say, I want one of those. So it's been a really exciting adventure so far. We have about 12 projects in design right now for a pretty small firm. So we're pretty busy, and a lot of my colleagues are really busy with passive house as well. So we've seen just kind of an exponential uptake in the past 3, 4, 5 years with passive house. So it's the industry is flourishing at this point. So it's called the Passive House Standard, and as I said, it's a German-based organization called the Passive House Institute in Darmstadt, Germany, and they have about 50 people in their staff, quite a number of building scientists, and it's an institute that really runs the program. They develop the building science behind it, and they do a lot of the QA process as far as helping make sure that the buildings meet the rigorous passive house standard. And I'll go into a little bit of detail on what that standard is, but also kind of what it means. But kind of the big step back is this is a slide from Architecture 2030 from Ed Mazria. And we found he did a lot of work on kind of discovering what the impact of buildings are generally, socially, in terms of carbon output. And he found that at least 40%, maybe more, of all global carbon comes from the building sector. That comes from manufacturing and the operations of buildings. And that's that way we all think it's either transportation or kind of other things, but when you put all the complexities of buildings together, they turn out to be the largest single impact in carbon. So that's definitely one of the core places to start when we look at reducing global warming gases in our atmosphere, even potentially sequestering them, which is becoming a popular topic. So carbon buildings on the energy side, or when you break it down from materials to energy, on your first year, it's a big lump of impact that we have, obviously from the construction of the building, and that can be quite significant. But then when we add on the overall impact of the energy it takes to make the building work, from hot water to heating, cooling, all the appliances, all those kind of things. Right now, our grid is still somewhat dirty. Even as it improves over the years, it's still a overall impact. And so the lower we the more we reduce the amount of energy the building uses, the better off it is for its lifespan, which can be a couple hundred years, honestly, the types of buildings we're designing. And then we can start looking at the materials that we built the building with too. And they should go in balance if we're really looking at the environmental impact holistically. And then just some ideas of the breakdown of energy use. Mostly, even in warmer climates, it's typically space heating is by far the largest impact. It's almost 50% of the mix in the United States. Here where I live in Colorado, it's about 54% of the energy use of a building. And then air conditioning is quite a fraction in Colorado. That's actually going up, unfortunately. A, because we're putting air conditioning in every building, of course, and B, because we're finding our summers and falls to be much warmer than before. So that's something that really helps focus on where the biggest impacts on that energy use pie to really design for. So what we really do is put a significant amount of resources into reducing the energy demand of the building in the first place. We don't start with the mechanicals. We don't hand that problem off, so to speak, to just a few people in the design build teams. That's really all hands on board. And I'll get into kind of the process, the passive house takes to deal with that. And then the other side of this, and we're seeing this quite a bit, I'm sure you guys are aware of where some of these building codes are going to, I should say. And a lot of it has to do with reducing or eliminating natural gas on site and doing all electric homes. So at that point, we're really replacing a lot of the ways that we heat the house, cook, things like that. We're doing swap outs with new equipment, of course, which is readily available now. But we also have to be very careful that we're not just upstreaming that problem, because we're still using natural gas quite often, especially at peak times, meaning when everybody's using power at the same time. We're typically using natural gas plants to provide that power. So we want to be conscious of that we're still looking at the overall energy usage of the building. And then of course, I've lived off grid for about 27 years. So I'm quite familiar with PV, but we don't really need to turn our houses into power plants. If PV is available, if it makes sense, then by all means do it. If storage makes sense for the house, by all means do it. But we don't try to make that as a priority. We try to do that as kind of an option, as a nice to have situation. And honestly, in a nice neighborhood, I'd rather see trees around a house than large PV panels. Makes for better neighborhoods, because we can put these PV panels pretty much anywhere, but a house is in a neighborhood in a very specific condition. So then, of course, I mentioned about the embodied carbon situation. So here's just a kind of a quick list of things that we try to avoid, eliminate, or reduce around building design when it comes to the embodied, or the amount of carbon output it comes from the making of the materials, transportation of the materials, and the application of the materials. And the big one is concrete. Concrete is always by far the largest single emitter in the world of any material by a significant amount, between 5 and 8% of all carbon is from the production of concrete. Things like steel, copper, aluminum, things like that can be quite energy intensive. I tend to stay away from foam insulations. I can build these high performance buildings with no foam. And there's a number of reasons for that. But one of the big ones is because of the embodied carbon situation. And then when we look at especially for larger buildings, complex systems that require a significant amount of equipment and things like refrigerants, things like that, the bigger they get, they become a significantly larger impact on the overall embodied carbon. And then even solar electricity, actually, solar panels take quite a bit of carbon to produce, ironically. I've actually done a project where we're looking at the embodied carbon of a commercial building I designed for a Venice Biennale architecture event. So what do we do instead? You may have heard of mass timber. That's becoming very popular in the commercial realm and hopefully more so in the smaller domestic realm. And then things like cellulose insulation. It's almost carbon free. It's a recycled material. It's incredibly good for the cost. It can't be beat for the effectiveness of insulation. So we use that. We use truckloads of that stuff. There's some wonderful materials, cork, wood, other natural finishes, stones, low process materials. But of course, there's new products coming along. There's like a hemp insulation company that just opened up in Montana that's providing a really amazing bat product. Wood fiber insulations. There's a lot to play with. It can be expensive at times. Other times it can be quite cost effective, especially if you're using something like a cork, which can be an insulator as well as a finished material. So that's very much a design intention. And then I'm going to just focus on the resilience side on fire, because we're seeing that out here in the West as being our primary issue right now. Outside of flooding, earthquakes, all those other things, fire is becoming an existential issue for neighborhoods within the Front Range, California, New Mexico, Rocky Mountain Inner West. So we're finding is that before we had a real kind of idea of what how to build towards fire, like maybe in the 2000s or the 1990s, 1980s, so on. We're experiencing significant fires that were hard to control from building from wildlands to building and then from building to building. And my personal home burned in the Oakland firestorm. And then after that, they started implementing wildfire codes within jurisdictions. They're finding that it had a significant and predictable reduction in entire neighborhoods burning as a result of these very kind of straightforward basic fire codes. And I'll go into some of the details of what those kind of houses look like and how in synergy with the high performance houses. So it's kind of you can have your cake and eat it too situation when it comes to resilient design and high performance design. And then we're also looking at things like pollution from outside. We want our houses to have healthy, fresh air inside. And how do we protect people from that? So how designing buildings and systems around that. Protection from the grid going out, it's great. Okay, we'll put in a battery system in the house. I live off grid. I lived on batteries for years and years. If the grid's off when it's sub-zero degrees, that battery's not going to last too long. So we want to make sure that the house in general is survivable even without a power system. Protection from overheating, the same situation. If the air conditioning goes out, is the house going to be unlivable within hours? And the protection from deep freezes. If the power goes out, how do we make sure that the pipes don't break, as we saw happening in Texas? And then kind of the smaller, more kind of nuanced things like mold. Mold can be designed out of buildings, but surprising how often mold creeps up in buildings, not just from like a leaky window or leaky roof, but from condensation. And that has a lot to do with the fabric of the building not being well detailed. So jump into the passive house side. So kind of the quick evolution of it was, we think about heating a home in the 19th century. It was just, using coal or wood essentially was our fundamental thing. And then we had stone exteriors or very light wood, uninsulated conditions. Then we put a little bit more insulation in our buildings in the 20th century, but we tended to come up with air conditioning, which spread across the United States like wildfire, no pun intended. And then we found out that we could build the same building in Florida as we could build in Montana, right? So, and that was due to a significant amount of dependence on the mechanical systems in the building. But in the 21st century, we're really looking at, and we're seeing code follow this very, very closely. That we're really looking at the insulation layer or the thermal boundary of the building being significantly more robust into providing small heating systems, cooling systems, and then dedicated fresh air systems. They're not the same thing. Sometimes we try to mix them, but it doesn't work that way. But the idea is that we're building for comfort, we're building for the longevity and less reliance on the mechanical systems, but still implementing right-sized, high-performance technologies. So think of it as a thermal battery, essentially, is what a passive house is. And here's kind of some of the inspirations of the first houses from around the world. There's many more other examples. And to the lower right-hand side is Passivhaus Frankenstein, which was the first official passive house built by Wolfgang Feist about 27 years ago now or so. And so it's still going strong, and we build our buildings exactly like that first one was. And there's a deep history to all these other types of buildings that informed the standard. And when it started, everybody thought a passive house looked like this, probably because it was actually building code where it was developed. In Germany and Austria, you had to have a building that looked like this. That vernacular actually worked really well for passive house. But this is not what passive houses look like most places. They look like this. They can come in all sorts of shapes and sizes, all kinds of materials, all kinds of use cases. So, and this is actually a pretty old slide now. I realize there's extraordinary amount of buildings out there. Probably, I'm going to guess maybe 50,000 buildings now that are built to the passive house standard around the world. And what are the characteristics? So it starts off with this idea of that simple form factor that you probably saw on that slide of the German Austrian buildings. And then the high performance continuous thermal envelope, airtight building envelope. So we need to make sure if we put lots of insulation in that we don't have air leaking through it and losing all the effectiveness. Like don't wear a parka without putting the zipper up. High performance windows and doors. The windows and doors is an incredibly important part of passive house, and that industry has absolutely exploded in the quality of products available around the world and the cost of them as well. Thermal bridges are eliminated. So a thermal bridge is where you have a material that can let heat in or out through the building envelope. And often that can be a steel detail, devil's in the details. It could be the windows, things like that. And that can add up to a significant portion of why we get mold in buildings, why we lose heat in buildings, and it can even lead to comfort issues. And then, of course, the constant ventilation system, the heat recovery or energy recovery system. So we constantly are replacing the air in the building, but we're grabbing that heat or that tempered air from the building and putting into the new fresh air. So we don't have a huge energy loss while we provide that fresh air system. And then the form factor, think of it as like this, where like if you just have your fingers splayed out in the cold, then they get cold quite quickly. Maybe you can wrap each finger and they'll keep them a little bit warmer. But if you put on a mitten and bring all those fingers together, then they can last a long time out in the cold without getting too frosty. And here's kind of a more passive house way of expressing it, where the more complex the shape of the building is, the more insulation we need for it. Now, we can make the buildings more complex, and we want to. We don't want just dumb boxes or boring boxes, although they're not bad. But we have room to play with, but it just means that we have to be more thoughtful about the amount of insulation. And the baseline is around the world is 4.75 kBTUs per square foot per year. And that's the standard way that we understand what the building performance is, apples to apples, universally. So we don't have people making claims in one place that don't compare to somewhere else. We want to understand a consistency in a verifiable quality of the buildings. This simple shape actually works really well for fire resilient design. So a more complex shape leads to more places for fire to get into. And that has a lot to do with the kind of thermodynamics of a fire condition, where we have hot brands in the front of a fire. And if they can find places to lodge into the building, even underneath solar panels, along dormers, around fences, or around all these kind of little conditions of the building, the more likely these buildings are going to be prone to starting a fire in that area. And like I showed this neat photograph of this. I think these are Tesla panels. We've actually wrapped the sides of them so they're protected from things like firebrands or even squirrels underneath of them. So it's little details like that goes a long way for the resilience. And then the air tightness side of things. For Passive House, we look at these, what we call a dedicated air barrier system. And so if you look at that middle slide, it says Intello in there. That's a material that's taped very, very tightly. It's a fabric-like material that has the ability to kind of intelligently work with vapor in the house, so we don't get condensation building up. But at the same time, it's airtight, and it wraps all the way around the building. So we get about 0.6 ACH 50. And in Colorado, often the code now is 3 ACH 50, which is pretty good. But going a magnitude lower than that significantly improves the quality of the building. And that's very much up to the builder to provide that. We do test the buildings. And then, of course, we put in dedicated ventilation systems into those buildings so that in the long term, people still have great, your building doesn't breathe, you breathe. So sometimes that idea of building breathing is actually kind of the opposite of what we really want a building to last a long time. We want a building that's dry and warm and doesn't constantly have air flowing through the fabric system to degrade it. But also in the firewise kind of condition, or the fire safety condition, when we look at smoke damage or smoke inhalation from buildings, I'm sure a lot of you in the West have gone through a summer or two where you've seen a lot of smoke in your own homes, how horrifying that is, to be honest, being unable to escape it. And so somebody in Canberra, Australia, built, I think, about 3 passive houses, at least 2 passive houses that were exactly the same. And that's right in the middle of the forest there. So they had some significant fires a few years back. And so he actually researched what the outdoor air was like, and then a regular house was like. And they're quite similar. To your left will be the red and blue line. So the red would be a regular house, and the outdoor is the blue line. But for a passive house, it's the yellow line. So about half of what the outdoor is, almost half of what less particulates than a regular standard house is. But when he actually, for his second house, they installed a very elaborate, or a HEPA filter system. Not an elaborate system, it's actually quite simple, but they actually put in something to deal with smoke level particulates. And from the red line on the right-hand chart, which was their passive house, their regular passive house, when they put the filter in to the yellow line, it actually, the house met during this extreme smoke event. It actually never went over the standard recommended rate for healthy home air. So the idea of controlling air becomes a significant part of how we think about the quality of a building. Then we hear a lot about net zero nowadays, and it's great. I talked a little bit about that peaker plant problem and heating demand in the middle of winter. That's our highest demand for buildings. At nighttime, when our net zero building with a lot of solar panels on it is not producing, but we still have a lot of, especially if it's an all-electric home, then we're looking at a significant gap in the amount of energy that the house can produce to how much the house needs. And it becomes seasonal. So we end up providing way more energy than we really need in the summertime and not produce nearly enough in the winter for most climates. But Passive House significantly shrinks that. So we need to provide less energy on site or near site for that net zero. But we're also really significantly reducing the use and dependence on grid dirty fuels when ours is not available. It also means that we need smaller, cheaper solar panels, and there is an actual, real carbon impact on the production of those solar electric systems. So it's not like they offset necessarily. Once carbon's in the air, it's in the air. You don't take it out again in most cases. In the way that we do this, the way that we start with Passive House is we use something called the Passive House Planning Package, which is an Excel spreadsheet, and it's a pretty elaborate, very, very detailed spreadsheet that gives us a dynamic look at the energy use of the building. In other words, if we change something on one side, it affects the entire building. So then we can offset that somewhere else. So there's a lot of give and take. It's really a true designer's tool that way. And really what the target is to get essentially in a kind of, let's say, a Midwest climate, that we want the house to be heated by the equivalence of a hairdryer for winter. So that's the kind of levels of low energy that we're looking at. Here's kind of an example of a project I have in Colorado Springs that's just about done. We're going to do the blower door test in a couple of weeks. And this project, we had a mountain view to the west, of course, is looking right at Pikes Peak. All the sun's to the south. So we need to make sure that we were properly shading the building, that we weren't overheating the building, for comfort and for the energy use. But in the wintertime, we can take full advantage of that southern sun while still being able to provide a good, clear view to the southwest and to the west of Pikes Peak, and then to the north of the Garden of the Gods. So it's a very dynamic process. You can definitely make passive houses for all kinds of conditions. You just have to be thoughtful about that process going as you go through that dynamic design system. And so ultimately the house is a simple shape. We're looking at two very small heat pumps, tiny heat pumps, the smallest I could find in the market, two 6,000 BTU units at 33 SEER each. So they're incredibly energy efficient, very cost effective. And then the city of Colorado Springs has had some issues with fire, unfortunately, so we couldn't use wood exteriors. Our window system is actually aluminum clad, even though it's a wood system, and it's quite well protected from fire. I'll show you something about that. And then in this case, we used prefabricated panels. So we built the fabric of the building was actually built offsite and then craned on site. Actually, I think our local PBS station did a nice little film on that process, working with a company called Collective Carpentry. And eventually, realistically, what we're looking at are really thick walls with really well installed insulation. So you got your frowny face, which is kind of the code building, and look at that insulation, all those gaps and crap. That's kind of, we don't want to see that in our buildings. And air flows through that type of material quite easily. So when we look at something called dense pack, if properly installed, it actually doesn't let air flow through it. It's protected on the inside. As you can see, there's a little gap between the drywall and the where the insulation starts, and that's our air barrier, and where we can run power systems like that. There's all sorts of ways to design these passive house walls. So we don't try to get too prescriptive in that sense. But at the same time, what we're looking for, these standard conditions for how the wall is going to perform. And that even includes foundation systems. For instance, to the left is my foundation for my personal passive house. Here's another slab foundation called floating slab foundation system. So we look at the details through the entire building. And windows, I mentioned earlier about how important windows are. That the idea of thermal bridging is significant when we look at how the buildings really perform both for comfort and energy. And so so we want really high performing windows. Typically, they're all triple pane. Um, they use spacers that are not made of metal, meaning what spaces the glass units apart are not metal, but a material that is quite resilient to loss of heat. And then they're put into frames, and they look complex and kind of crazy, but it makes it a lot harder for heat loss through the entire building system. Then the windows are sealed typically about 3 different times. On the outside, there's one seal. There's an seal in the middle and a seal at the bottom. And then the way that they're installed actually affects dramatically how well the window performs. So if you're going to pay a lot of money, put a lot of energy into the window, you also want it to perform really well. So if you can see to that slide with the rainbow colored stuff, that higher U value, the worse it is. We're looking at kind of the metric system. U values are the inverse of R values. So higher U value, the worse performance. So when the window is really inside the wall, we have much more exposed wall area. Details. The frame is not as effective. But if we put it on the outside, it's definitely much more effective, but it's not ideal. It's not the perfect version. And then if we put for instance, the window right in the middle of the wall, so it's kind of those trade-offs. And there's other reasons why you'd want the window either on the middle of the wall or on the outside of the wall. But it just gives you a kind of quick glimpse on how far down the rabbit hole we go with these types of buildings. And then for the Firewise thing, and this is kind of a personal experience, or, as I said, a family's house burned in 91. I live in a forest. Cameron Peak fire came right up to our building a few years ago. And I've been thinking about fire for years and years and fire resilience. And windows are a big part of that. We've seen a lot of buildings, even buildings made out of concrete form, stuff like that, burn in fires here in Colorado, in Larimer County, where I live, because often things like the windows failed and they crack because the outside radiant exposure actually expands the window and it breaks the glass. That can happen quite quickly, and it can be quite tragic. Or the frames are exposed, and those frames can burn from fire. So in Passive House, one of the details for the triple pane windows is we actually bury the frames and the insulation to improve them. They're triple paned. They can be tempered. So you're significantly improving the time that the house is resilient to that fire front. So that's kind of an extra plus on top of kind of just the overall energy and comfort side of it. And then for the mechanical systems, we're looking at heat pumps, right? We're all hearing about heat pumps in the media. We're seeing heat pumps being installed in lots of new communities, lots of new buildings. We're seeing them replaced in buildings now. It's really exciting to see that change. We're seeing states and probably the federal government give us a lot of money for for installing heat pumps. And then there's two kinds. There's the air source and ground source. And typically we're finding now that the air source heat pumps are as effective as ground source heat pumps in terms of providing comfort and somewhat close in the energy efficiency of them. Ground source heat pumps are probably most cost effective for larger buildings where they have a balanced load between cooling and heating. While if it's a primarily heating condition, ground source heat pumps may not be the most effective compared to air source heat pumps. So just be careful that there's no right answer for all of these, even though lots of people have opinions about them. And then sizing of these things. Even if you get the best technology, if it's not properly sized and designed for the building, it's going to perform like crap. It's going to be expensive to install because it's larger, probably more complicated. It's going to be much more expensive to run. So everything needs to be right sized, measured correctly, and properly accounted for as we develop these buildings in the future. And of course, that's a big part of what Passive House is, to make sure that that does match. And then matching the energy consumption with renewables. So for instance, like in the future, we're probably going to be heating water as we make peak energy, maybe even on site. It communicates with our batteries. So the first thing of the smart home was light bulbs and talking doors or whatever fits our fancy. But kind of the smart home 2.0 I see is how we use energy flows through the building, when it's available, when we can store it, when we can use it. Those kind of technologies are probably going to become much, much more prevalent in the next 10 years or so. So watch out for that. And then kind of the bigger picture, what the whole passive house thing is based on is this idea of primary energy renewable. We're building for the future. We're building buildings that will be here for 200 years. And what does the energy grid look like? And the energy grid using renewables is going to be vastly different as a technology and approach than it has been with traditional coal, natural gas, biomass types of systems, where we're going to have a lot more fluctuation in the grid. So we want our homes in our buildings to be able to be somewhat responsive to those conditions where we make a lot of wind or a lot of sun or no wind or no sun or a combination of those two. And then we'll have online storage, but storage is actually quite technically difficult and very expensive. So we don't want to be 100% dependent on storage. So think again, the house is a thermal battery, and then it's just sipping energy when it needs to. And that's basically how we're designing buildings now, is based on those future conditions. And that's the energy modeling that we do is based on this idea of primary energy renewable. And then carbon buildings. So we can build with all sorts of cool things, these high performance buildings. I showed you like the cellulose earlier, but I have a project up here in the mountains that's going to be using something called an eco cocoon panel. And again, it's a prefabricated panel, but it's made out of straw. And it's in straw that's very precisely installed in the building, so it's not like a straw bale. So it's a very consistent product. It's certified by the Passive House Institute, so we can rely on its thermal properties, and then we can finish it in all sorts of different ways. And it's a carbon sink. It actually will take carbon out of the atmosphere and fix it into the building structure of the building. And then straw, yeah, straw burns. Straw actually doesn't burn. When it's really packed well, they did some tests. It's a European building, so they're doing European tests. And they could rate it, if you have 1 inch of gypsum board on it, you can get more than 3 hours for a fire rating for it. Just with a clay finish, which is often what we use on the interiors of these buildings as well, we get at least a 2-hour fire rating. So they're extremely safe. I'd say they're much more safe than current standard building products, especially the foam products. But the idea is that kind of the synergies of materials, performance, and safety can come into these building systems. And then finally, and I didn't really talk about this, I want to send this at the end of the talk, was ultimately this is all about comfort and quality of life for the people who are investing in these buildings. For instance, you can't, we almost need to hire artists to talk about this and to express what these buildings feel like, but they feel different. They're thermally neutral. What does that mean? That means that I don't have hot spots. I'm not hot on one side or cold at the bottom at the floor at my feet, and then hot at my head. So they're not stratified. The buildings are quiet. The buildings are consistent in temperature through the day and night, pretty much. And it doesn't matter where you're in the building. You can be right next to the window, or you can be in the core of the building. You're going to feel quite similar. The fresh air system, you're always breathing in air that doesn't seem stale or a little stinky, right? So that's nice. And we have control of all those elements through the science, the building science for Passive House. And it's just kind of a long list. For instance, like the humidity or the airspeed of the ventilation system, the radiant mean temperature or asymmetry between different parts of the building, including the frames of the windows to the wall, to the floor, to the ceiling, have to be very close to each other through the coldest of times, minus 15 degrees Fahrenheit. The building itself has to be within 3 degrees of all spaces of the building. The mechanical system has to be very quiet, 35 decibels. You're probably not even going to hear that unless you're right next to the equipment. So very, very quiet. That's kind of the first thing people actually comment for my passive house is the quietness of the space. We usually like to change the air at least once every 3 hours, typically more than that. And we take the stale air out of bathrooms, kitchens, mechanical rooms, other places where we want to get evacuate air rather than having it mix in the house. Same with carbon dioxide. We don't want carbon dioxide, especially in bedrooms, to pick up and people get sleepy and kind of lethargic once it gets to 1,000 parts per million. Once you get into commercial buildings or schools, that makes a big difference, like in a classroom setting, to have low carbon dioxide levels. And then condensation is a main thing as far as like the health of the building and the well-being of the occupants is that mold grows where there's water. So eliminating condensation is a significant part of longevity and the well-being of the occupants. High efficiency fresh air exchange, we kind of go back to that over and over again. But another kind of thing is that we don't want to put cheap equipment in that's not efficient in that heat exchange, because if you put in cold air into a bedroom, it could be fresh, but if people feel a cold spot, they're going to inevitably turn that off, and now you don't have a fresh air system anymore. So that has to be really quite thoughtful. And then extraction of air from areas of concern, I just went through that earlier. Bathrooms, kitchens, things like that. We want to get that bad air out as quickly as possible. But it's really personal. It's about coziness, kind of that warmness, that feeling side is what people really respond to. So we have all the science behind it, and the ultimate kind of result is that sense of coziness and protection. And this is a photograph of a good friend, Jessica Grove Smith, and she's actually one of the 4 heads of the Passive House Institute now. She's an actual building scientist, and I can't tell you what a joy it is to be able to spend time with somebody who spends a career and a PhD understanding the actual science behind how our buildings work and developing a process and standard so that we as designers and builders are not making it up as we go along or saw something we saw on the internet or read in a book. We actually have a system that we can work with that's consistent. And then we have a verification process where we have a third party helping us along and verifying that we are building to what we say we do. And that makes a gigantic difference in the industry. It can be somewhat chaotic in claims and hard for clients and other people to really understand what's real and what's not real. So it's kind of the quick conclusion for an overview of those kind of criteria around what high performance building does. And again, my contact information, Andrew at hyperlocal.com, or you can just go on the website, hyperlocal.com, see some of our work. So thank you so much for your time, guys. And I'd love to ask no questions too dumb or too technical. Oh, we have no questions. I know somebody has a question. So what are the questions we typically get? So the passive house thing, why is it called passive house? Actually, passive house means passive building in German, passive Haus. And house in German means building. So they always started off with the idea that this was a standard for all types of different kinds of buildings, not just houses. The United States is mostly houses now, but one of the projects I showed was the Corona Tech Tower, which is about 23 stories in New York City, is a dormitory building, essentially. That's a passive house. I think it's topped out. I'm not sure where it's at. It's probably close to being moved into in Boston, there's a 55-story building right in downtown that's going to be a certified commercial office building. There's another passive house that was finished about 3 years ago. That's a hospital in Germany, and so it's quite interesting to see how elaborate the building system's getting. I developed a passive house, multifamily 8-story building for Los Angeles as part of a Venice Biennale. And I was looking at like the carbon question is how can we use low carbon materials and passive house and renewable energy on site and calculate the real carbon impact of buildings. So, so it's somewhat dynamic in that sense. So let me I have a question here. Can you talk more about right sizing? You mentioned in the tiny heat pumps for the home. We typically think we need a large HVAC system to stay comfortable. Are there studies about the fractions of energy passive house takes compared to? So yeah, passive house probably uses probably about I'm going to say this is a very general term, probably about a sixth the size to a fifth the size of energy. So BTUs for a passive house, let's say it's about 10,000 BTUs for a passive house, would be more like 6,000 BTUs for a code built house now. But but it's even more important, and this is kind of where the industry is completely upside down, is that HVAC systems that are oversized lead to very uncomfortable homes. Think of this, and we've all experienced this. You're sitting in a house, it's at nighttime, it's a cold night outside, and the furnace kicks on, and the air gets really dry and really hot within say 10 minutes. And then in another 10 minutes, it turns off again and starts getting cold. So you have the seesaw effect. So it's short cycling essentially, because what's happening is that the furnace system is too large and the house is losing too much heat at the same time. So it's leading to this point where you're getting too hot and too cold at the same time because of the oversizing of the equipment. If it was a smaller furnace or a two-stage furnace that could just provide the right amount of heat at the right time, then you're better off, and you're probably getting more efficiency out of it. And the same thing goes for summertime with cooling. This is especially true. You know that term clammy, like a clammy building? You experience that? Clammy buildings are almost always the result in summer because of oversized cooling equipment. So what's happening is that you can make air cold really quite quickly with an oversized cooling equipment, and it can stay cold. I don't know. People call that comfortable. I personally don't find a 64-degree building in the summer to be comfortable at all. It gives me headaches. But besides that, if that system can cool down the building really quickly, it can make the air colder. But a lot of comfort is because of the humidity of the building. So if it's not providing enough time for air to go over those coils and to squeeze out the moisture in the air, you're going to end up with a cold, clammy building, which can be quite uncomfortable for people. So oversizing equipment is actually more dangerous in terms of comfort than slightly undersizing equipment, it turns out. So it's kind of an interesting scenario. Oh, no, I can't hear you. Somebody's saying something. But before, I think Jessica's trying to get on, but I got another question. Before, you talked about protection from the environment and what happens when the power goes out. Can passive house stay comfortable for long periods of time with little or no power? Yeah, that's kind of its bread and butter. Passive house is its ability to uh, create a habitable situation when the power goes out for a long time. I'll start by saying is that I turn on the heat in my passive house maybe a couple dozen times through winter. That's when I actually need um, heat. But when the heat did come off, we actually had some guests who were writing a music album here, and this during that big freeze that took Texas out. Here in Colorado, it was about minus 20 degrees, and I designed my heating system connected to my hot water heater. My pipes froze outside of the house, going to the house. So all of a sudden, I had no heating in the house. So the guys were in here for days on end with minus 20 degrees. I think the high was minus 5 degrees for about 2 or 3 days. But they just by living in the house, by using the building, they became the primary heat source for the building. So it never actually got below, I think, about 57 degrees, which is not comfortable necessarily, but they put on the coats and they were pretty happy, to be honest. It was kind of amazing how they were able to live and still write their music, create their album, even without any heat in the most extreme weather I've seen in Colorado. So to me, that was a proof that the passive house definitely works in those kind of conditions.
Hi, I'm back.
Scott, you're back. Hello.
Oh, that's great. So you said that the people in the house making music, they actually became like human heaters for the house?
Yeah, in passive house, we calculate how the house is used as a heating source. So the cooking, showers, your pets, the way you use the building, your computers, all that is calculated as a heating source for the buildings.
And when the power went out, just the human beings in there kind of kept the house warm for a long time?
Yeah, exactly. It was because the hot water system couldn't provide any heat to the building. So we're totally reliant on activity of the building itself. But also because we weren't losing a lot of heat over those days. So it was quite habitable. We didn't have to worry about, I can leave the house for months on end in the winter and don't worry about pipes freezing and the power going out. So it's.
And you weren't losing heat because, like you said, I love the examples you gave. It's like the house has a parka, and of course it's airtight because you zip up the parka, so you weren't losing that heat. That's great.
Yep. It all works as a system.
Well, thank you, Andrew. I learned a lot. I hope our viewers learned a lot. And we don't have any other questions. We might wrap up. Do you have anything else you want to share?
No, I think that's good. We do have a link if people are interested. I don't know if you want to share that link for the Restore House project that we did a talk on.
Yeah, that would be great. So this is a link to the Restore House project that Andrew did for Colorado Renewable Energy Society. Let's see if I can share. Honestly, I'm not sure how to share the link.
Okay.
I apologize.
Maybe we can put it in the YouTube chat.
I will put it in the YouTube chat. And for EXP agents, I will also put it in the chat under the EXP Climate Action Network. And if you're not already a member of Climate Action Network, please do consider joining. We host speakers like this often, and education and marketing about everything related to the environment and climate action is what we do. So thanks for joining us. And I had a slide to share about our next speaker. Next week, oh, there it is. How to have your yard and eat it too. Landscapes for edible food. So we hope that you'll join us next Thursday, April 13th. And as I mentioned, we have a lot of exciting stuff planned for April for Earth Month. So everyone, happy Earth Month, happy Earth Day. And thank you for logging in today.